Remember now, like the states. Let us talk about if it's a motor vehicle or object moving a motor vehicle. Then the one state is the speed, one state is the displacement. And if you're minimizing the energy used for those things, then you minimize the amount of gas you would use to get from point A to point B. Right? So there are times when that is your consideration. Right? And that is your only that is the only consideration that this thing is concerned with. Minimizing the energy.
Okay.
So you might be interested in doing only that. You might be. Right? So for example, again, let us say that you have your furnace and you're heating your furnace. Right? You want to get from there to 1100 degrees C with the minimum amount of gas or whatever it is that your furnace uses, or minimum amount of current, electricity, minimum amount of power. Right? So it's going to give you a trajectory that minimizes the amount of energy that you would use in a particular system. Make sense?
Yes, sir. Yes, sir.
All right. So that's the first thing that we need to try to make sense out of, because I did a whole course on this at university. It's me as a lecturer to do the course on it, and halfway through the course we drop it and leave the Indian them and the Chinese them. Plus 2x plus lambda is also equal to 0. Problems. And then, oh, sorry. When differentiate this, you get 1 plus lambda also equal to 0. Not so much of a problem again. And you'd have to differentiate it to lambda x plus y minus 4 equals 0. And then in maths class, like I said, I'm not attempting to solve it. X, y, lambda equal so this will be 2, 2, 1, 2, 2, 1, 1, 4, 0. There's no lambda in this equation. Is equal to, this is 4. You carry this away as minus 1 and 0. So you would solve this. Alright, so the whole entire process is same like you do when you're doing calculus, one single variable calculus, but you would put in the sub constraint and then you would differentiate it, make it equal to 0, and then solve for x, y, and lambda. And that would give you the value of x and y. That would be the minimum point on that function. All right, and that is called Lagrange multipliers. So, like I said, we're not interested in solving this. We're just showing you what is done to minimize a function. Now, so make we go back over to here. So we know that the AX plus BU is that's the equation for the system. And the JU that we're trying to minimize is the energy of this system, input energy, and the energy of the state. So we're not just minimizing the energy, but we're minimizing energy that it has to obey the equation of the system. So that is why it is subject to x dot equal ax plus bu. Now, no attempt will be made by me to try and do what I did over here. You see that is the same function. It having x squared, having u squared. And so forth, and ax and bu and all those type of things. So it has in all the things, and then would add the lambda. So suffice it to say, that is why I dropped the course, because the lecturer tried to solve it in class. And he was solving for about 4 weeks. And I dropped it at the end of the 4th week, the course at the end of the 4th week, because I had no interest in solving the equation. And the reason why I have no interest in solving the equation, because somebody solved it already. It's engineering made, not in maths. So if somebody solved it already, then we have to solve it again. All right. So this evening's discussion is not about solving the equation. It's just understanding what it is that they are trying to do, and telling you, say, this is the method that them use, and do it. You have a function, multivariable function subject to an equation. Then you have to use Lagrange multipliers, put the lambda and it differentiate everybody, make it equal to 0. You're going to end up with a matrix equation that you have to solve. All right. So that is all that we are telling in the motivation. All right. So so the basic thing that is to understand what it is that we are trying to do. We're trying to minimize the energy of the state, and the minimization that we're going to do is going to be subject to the constraint. It has to obey the system equation, ax plus bu, which is the system equation that describes the system. So the input-output relationship, or the state-input relationship. So we're trying to minimize that, and we would use Lagrange multipliers. All right. So I'm just going to say now that attempting All right. So when we apply the Lagrange multiplier and everything like that, we end up with a system of equation that we have to solve. So let me just deal with go to that, and
So what was the name of the last thing you wrote, sir? The R word that you had a while ago.
Matrix Riccati equation. You see it come back up. I just find it there.
All right.
me put it back up now. Sorry, 1 second. Now, I was looking this up today, and then the first thing I read is this thing up here. So let me just highlight it and point out. So these things change year in, year out. So could I use it last year? No, them not recommending so we use it. So we must use this function instead. So I will go to this function after I explain what the care function is. I'm not sure why it's not recommended. Well, yeah, I know why it's not recommended, but let me explain what this is now. So the function that we said was ju I'm supposed to have x in there, but so it's the minimization of the energy subject to the constraint that x dot is equal to ax plus bu. Now, when you try to attempt to minimize the equation, you end up with this equation. Oh, I spell it wrong. You know, it's RICCAT. I have RICATTI. Riccati equation. So, in attempting to solve the equation, you're going to end up with this equation that you need to solve. Now, it is a non-linear equation, which is why we have to use MATLAB and solve it. So let me just point out some things that we need to bear in mind. So we're solving this equation for the x value. So we solve this equation for the matrix x. And then now the gains, when we solve for the matrix x, the gains, which they're calling g, or you can call k, is given by that function. Now R inverse, B transpose, we know B would solve for x. And so we need to just talk about these two. The R inverse and the E. Now the default values for these as is seen is so it's 1 Ri. So basically what we are going to be solving for is the gains of the system is B transpose times X. So what we are saying now, we have this equation. A is the system matrix. B is the input. So what is Q? Q is the matrix C times C transpose. Do I have it right? No, sorry, the other way around. C transpose times C. So Q is equal to C transpose times C. R is 1 and X is 1. And then the gains that would solve this equation, which is the Riccati equation, would solve it to get X. And then the gains that we want is going to be R inverse. R is the default matrix I, unless we are told otherwise, or want to use otherwise. And E is also I, unless we are told otherwise or want to use otherwise. All right, now, so what we are required to do We soon go to the I care, because remember now, them telling us this year, the care is not recommended anymore. So the X, the L, and the G, like we said, is the gain of the system. L are the eigenvalues of the system, and X is the solution to this matrix equation here, matrix Riccati equation. So, so if you remember, I ended up with the simple one. I ended up with a matrix X, Y, and lambda equal to something. So the matrix equation that we have to solve is this, and we have to solve it for X. All right. So when they do them differentiation and do everything and simplify as much as possible, this is the equation that we have to solve. And it is impossible to solve it by hand, so we have to use the computer and do it. So that's why the computer is going to solve for X, solve for the eigenvalues of the system. Now, why you would need the eigenvalues of the system when you're looking at your solution is that you'd want to know that your system is stable. If your system is not stable when you do the solution, then it don't make no sense. All right? And G would be the gains of the system that would minimize the energy. So you want to look at all of those things when you are going to make the solution. So for us this evening, all we are saying is that if we're going to find, we need A, we need B, we need Q. We need to define those. And we say Q is equal to the output matrix transpose times C. So X, L, and G. So let me look at an example. So it is simple to use really. So they give the equation, and so here's one question that I honestly don't know the answer for. I've been looking and been trying to find out why they use R equal 3. Because the default value of R is always 1. And I don't know why the default value of R is equal to 1. Somebody can do some research and find out. I think somebody just pulled it out of a hat somewhere. But all right, so they are just doing something arbitrary here. R equal 3. So you have A, you have B, and we say you need C transpose times C to get this is my Q. So as you can see, they put XLG, they list out the system, list out XLG equal care AB C transpose times C, which is Q, and R, which them list as 3. And they're going to get the X, which we're not really interested in. The eigenvalues, which we are interested in. Now, these the two types of eigenvalues. It asks for, it gives the eigenvalues of the system. So if you look at, this is the matrix A and it gives you the eigenvalues of A. Now, this is not stable. So the thing that you had initially is not stable. But when you apply the gains to the system, this is the G would be the gains. And the new system, when you apply the gains to the system, what we are asking is what kind of system do we have? And you see that now when you apply the gains that we're going to show you below, the new system, the values mean that it is stable. So the solution that we have is a stable system. So therefore, you know that stability means that it's going to go to a final value. All right. So that's why I said that you're interested in this in it in L. And then the other thing that you'd be interested in is your where is it? It's supposed to give me G, X and L. I didn't say G. X, L. It's supposed to give me G. I think this is a mistake that they make. This is supposed to be the gains. Well, in your closed loop, eigenvalues L equal blah blah blah. So this is how those the gains are. Mr. Cooper, calling C Cooper. All right,
Cooper, sir.
all right, tune me out.
No, sir.
No, Mr. Cooper. Sorry.
Yeah.
I know another class with Cooper. Campbell. Gosh. There's another class with a Conroy Cooper.
Yeah.
We're not functioning. All right. So I would like you to put in this because I don't see the gains of the system that you're supposed to get. I see L and I see X. So L, I say, represent the eigenvalues of the new system. X represent this matrix recursive equation solution that you're supposed to solve for. It's like when you solve for X and Y and lambda. So X represents the solution that you get, the matrix solution that you get. But I don't see any G here. So I'm going to ask that we run this.
In
I no
MATLAB.
longer have MATLAB on my computers. And 3. So as it is, 3, 2, 1, 1, exactly as they have it here. As they have it here.
All right, I'm going to write it.
You can define Q before. You can define Q equal C transpose times C. Or let me work it out. 1, -1 times, sorry. 1, -1 times 1, -1. For that equal to, so that 1 times 1 is 1. 1 times -1 is -1. -1 times 1 is -1. -1 times -1 is 1. So this is what my Q equal to. So you can define that matrix as Q equal to 1, -1, -1, 1. All right, Q here instead.
Write Q where, sir? At
As you can, if you define Q,
at that line there.
you define Q, then you can just write instead of C transpose times C, you can just write it as Q.
After we write R equal to, we define the Q. All right.
Huh? So -1, -1, -1.
All right, the Q now. So just write Q is equal to, what is that? 1, negative 1.
1, negative 1, semicolon, negative 1,
Negative
1.
1.
No, share screen between them. So, let me, gonna see this. Oh, for you to share the screen, you have to make you the host, right? Keep on forget.
Something like that, sir. I think I can just allow participant screen sharing.
Huh?
I think there's a thing there where say allow participant screen sharing.
Yeah. I'm trying to find it. Oh, okay, so allow this computer record to cloud. Real. Share sound, optimize video clip height. Yes, for security. Wait, my profile picture share screen. Hello, yeah, all right, cool. Yeah, you're supposed to can share screen.
You have to stop sharing your screen.
So it's supposed to be X LQ equal XLG, sorry, equal care.
Is care or I care? I care this time.
CARE. No, care. No, care. We have to explain I care first of all. And that is command A, command B, command Q. You can just click the top one. Well, A, command B, command Q.
That's it.
Mm-hmm. No. Oh, yeah. Until percent. All right. So the part that was missing was the Q, the gains of the system. That wasn't in the example. So these are the two gains that you would use. Right. So it gave L what they gave us was the eigenvalues of the old matrix, and that wasn't stable, and then the eigenvalues of the new matrix when you apply the gains to the system, and that new matrix L, you see the two gains are negative. So therefore, because it's negative, then we know that that system is stable. So it stabilizes the system, and you have the gains that you would use to get the minimum energy for the stability of the system. All right. So we proceed to the next example. All right. So let me just go back and then go back to the next example. So which part you got? so let me go to the I care one. Give me 1 second. I'm just looking. To see why them say it's not recommended. So look here now and then. Enter A and B and C, and let me see why the care function can't use, or them not recommending the care function. Where's my thing here?
So,
Sorry, let me tell you what no, look at we want you to look at the equation first. So let me just put it back on the screen.
okay. All right.
All right. So you see in this equation. So this is the A that I want you to enter, the B and the C. Previous years I would have tried solve this equation, which is the matrix Riccati equation, by hand, and then halfway through the balance, then we can say, all right, we solve it by using the matrix method. So this is the matrix that we want to enter: A, B, and C.
Okay.
So then when you enter them, and then we use the care function, and then we see what is it that I care supposed to do. Then when you type it in,
Yeah, type it.
huh?
We're typing it. All right, ready, sir?
Yeah, so share. So type in Q equals C. C with the C transpose, which is the times C. No, not that. It's a apostrophe. Times C. All right. Oh, come and see.
Yeah, come on.
Use capital C.
Yeah.
All right, but it correct itself. Well, wonderful for MATLAB. All right, so now type in the care function and we'll see what it is that they're not recommended. So this is just the XLG equal care.
So wait, the care or I care?
No, care.
Just
You type in I care after that, we'll see what happens.
all right.
Care. So it gives you the gains. It gives you the. All right, so type in I care for me. So the same thing, XLG equal I care. I think you probably have to type in more variables. This is the same response.
Yeah. But when I get
according to them, I care supposed to give. No, the gains are the same. G is the same. Look and see. G is the same.
I think so. Wait, G
no.
So
Wait.
Switch one. You switch one, man. G is now L and L is now G.
Yeah, L is now G.
So which one is right? The I care. Since then recommend it.
Let me sorry, give me a second. Let me read what them. Give me a second. Oh, no, the I care gives you X, K, L. So the G is in the middle and the L is at the end. So there's no, the gains, the second thing that you see. And then the eigenvalues of the function, the last thing. So the second thing on the screen is the gains.
Even though it's a L equal?
So yeah, that is what they're calling the IQ function is giving you the gains, and the Q is actually the eigenvalues of the system. But what they were saying is that because most of the time people working with matrices that are large, 200 by 200 matrices and all them kind of thing there, then what will happen is that the IQ is supposed to make the computation a little bit more accurate. All right, but in this particular case, you don't really change anything.
All right, so where's that, sir? The gains come last. Wait, so just go over a bit. Which one of them is the gain?
the gains of the system are the ones with the all right, so X, the L in the I care is the gains, and the G is the eigenvalues of the matrix. So that's what you're highlighting there is the gains. And this thing that you're highlighting are the eigenvalues. I care switch around the two of them.
Okay.
Yeah. So it switch around the two of them. So you're going to end up with the gains being the second function and the eigenvalues being the third function. Whereas in the original care function, it is the other way around. Right? So that's the only difference that I see here. I don't know. I'm wondering.
They should have changed the labeling then, sir. The L should have changed to G in this case. In the first case.
Well, what them have as is XKL.
Okay. So the I care is that's what I would say the I care is more preferable then. Well,
that's what they are saying. And up to last year, this time it wasn't. But now this year it is. All right. So all right. So maybe just work through one example and then one final example, and then discuss what we're going to do going forward. Okay.
Maybe it's also definite form check. Are you going to count this for science of data?
All right. So let's look at this problem here. So we have to find the transfer function. This is 1 over s. This is 1 over s. Right, okay. Well, this is 1 over s. 1 over s. This is 1. This is 1. This is 1. This is 1 over 2s.
Sir, we're not seeing your screen.
So we would do this. Oh. I was sharing. Sorry. Share screen. Oops. Alright, so the problem here. Alright, so we're trying to find the transfer function for this thing. So this is 1. This is 1 over s. This is 1 over s. 1, 1, 1, 1 over 2s. So we divide this in 2. Call this one g1. Call this one g2. So I would say g2 is equal to 1 over 2s over sum of these two, which is 1 plus 1 over 2s. That's 1 over 2s over 2s plus 1 over 2s. These go. So that's equal to 1 over 2s plus 1. G1 is equal to, so these two are in parallel. So it's 1 over s plus 1 in parallel with 1 divided by, this is 1 plus 1 over s. So this is 1 over s plus 1 times 1 divided by 1 over s product over sum plus 1 divided by everything over common denominator s plus 1 over s. We have to put the minus sign somewhere. So this times 1 would be common denominator is s, 1 plus s over 1 over s plus 2. This is 1 plus 1 is 2 multiplied by s over s plus 1. So this is 1 plus s over s over, this is s, 1 plus 2s multiplied by s over s plus 1. That equal to s over equal to s over 2s plus minus. So the transfer function is equal to g1, which is minus s over 2s plus 1 times G2 1 over 2s plus 1. So that equal to minus s over 2s plus 1 squared. That's a transfer function. Let me multiply it out. So that is minus s over s squared is, what is that now? 4s squared plus 4s plus 1 when you multiply it out. Now if we divide by 4, so it's minus a quarter s squared plus s plus a quarter. Alright, so if we write it down this now, we don't really need to go MATLAB to go write down this as a transfer function. But so let us assume that you remember how to write it down. My x is going to be, there's no s here, there's a minus a quarter x s, and there's no constant term. My y is going to be 1 a quarter. And so first thing, B C D equal transfer function to state space x, y. So it will write it for us. And then we would write down that Q is equal to C transpose times C. And then we would write down X, L, G for gains is the care function. A, B, Q. What I was going to say is that instead of doing that, we could write down our X dot is going to be equal to 0, 1, negative a quarter for this one here, and for this one here to be 1. Plus 0, 1 u, and y is equal to 0, and the s is negative a quarter. So this is what MATLAB going to give you this upside down, backwards. Alright, so we're going to type this in and see. Now, notice something here, and it's something that you will notice, is that this finding the transfer function is always way harder than finding the gain. If you know the transfer function, then the rest is easy. So finding the transfer function is the problem. right. So I'm going to ask Mr. Campbell for share screen again and run through this particular thing.
Yeah, I was putting it meanwhile there, I think. So we actually have it. The X and the Y and,
Right,
and
so
the,
please stop share.
Alright.
Oh, so you start typing it already.
Yeah.
So please stop share so we can share the screen. So you don't put them in already. Alright, so we just make sure. Okay. And is use care or I care?
Care.
Alright, so as you see that it's upside down. A is upside down, B is upside down, and C. Wait, C turn the right way. That means we probably do something wrong. C is this. Did I have a 0 and then a quarter over the next side? For C? No, that right to know.
I don't remember what I have there.
It A is upside down, B is upside down. Alright. So when you enter them in MATLAB, you see that it will give you the gains that you would use for the system. Alright. So now, thus ends the matter discussion for Modern Controls 2021. So what I'm going to ask you to do now. So the first thing is that we are going to take that the paper that was produced by some people in the Middle East or Far East or whichever part, and we're going to try to fix it up. So two things that we are going to ask you to do. Well, all right. So let me find the paper. Hopefully, I have it here, and I didn't leave it at school. Give me 1 second. Let me see if I find it. So let me just all right. So this was paper produced by some Indian persons. So for your project, we are going to use this paper first problem that we have, well, we had wanted to do it something practical. But the same thing, introduction, derivation of the system dynamics. You'd like it to do a better derivation. I will send you the material for you to do a better derivation. And then they use a design of controllers, so they talk about the PID control. Most ancient originated by Ziegler and Nichols, blah, blah, blah. And so them can use Ziegler Nichols method. But then what you notice that they did here, I think I'll be wrong paper. Give me a second, let me see for the I'll send it to them. But anyhow, so it's the same structure. But what I want you to do is not just when we are about the transfer function, look at derivation of the transfer function. Then the next step in the problem is that I'm going to ask you to try all three methods of control that we say: pole placement, PID, and minimum effort control. And then we're going to put in, same like them, simulation results to see what is it that we get when we apply a step input to the system. Right? What are the results that we get when we apply a step input to the system? And our conclusion is to be which one we think is the better one. If you're going to type in references, then see the reference then here. All right, I'm going to, there's two papers. So we're going to do the white man approach. Let me find the other one. All right, so here's the other paper. I'm going to send the paper in the group and we're going to have a week by week discussion. So this is another paper written by another set of Indians. Go for the top. So the thing about it is ball and beam system. So I'm going to post in the group the video of the ball and beam system that I'm also going to post a derivation that was done. So what I'm going to ask you to do, just like a lab write-up, but this is a paper write-up. So you can form yourself into groups and discuss who will do what. But we're going to talk about the ball and beam system, the introduction, modeling of the system, so how we derive the transfer function for the system, which I will send to you a derivation of how the system was derived. Then we're going to ask you to talk about when you get the model and the transfer function from the model, we're going to apply the three different methods of control that we talk about: PID, pole placement, and linear quadratic regulator. And then we're going to come up with the conclusion. And like I said, your references are already written. So I'm going to put these two papers in the group so you can have a look at them, not read them, have a look at them. And I'm going to put the derivation. And so I'm going to ask that you put yourself in groups and put yourself so that you can produce a paper. And that will be the lab grade.
How much for a group, sir?
Now for the test, here's how it's going to work. I'm going to put a exam paper in the group as well. That exam paper I need you to go through and do it. And then we're going to get a 20 question midterm and a 30 question final. The 20 question midterm and the 30 question final will be based on the paper that exam paper will be sent in the group. Following?
Sir, can you repeat, please?
One more time.
I'm going to put a paper in the group. I need you to work it out. But I'm going to give you a 20 question midterm based on the paper. Then I'm going to put another paper in the group. And then you're going to get a 30 question final based on that paper.
Okay.
Okay, noted, sir.
Capish?
Yes, sir.
So your 20 question midterm, your 30 question. Huh?
Sir, what's the maximum per group?
Per group?
What's the maximum per
4,
group?
5?
5 works.
Yeah, 5. A 23, I want to see here. All right, so 5 maximum. So put yourself in some group and send me the list of the group. And so I'm going to send those things into the group. So there's nothing else that I have to talk about with respect to anything in the discourse. It's just the problem. So next week, we're going to talk about we just log on and see whatever issues you have to talk about.
Sir, you can repeat the details of the group activity.
Yeah, but we're ready to go. So I wanted to, I'm going to put 2 papers, you work on those, and then you do a final exam and your midterm exam. One is a 20 question multiple choice, one is a 30 question multiple choice based on those papers that we're going to give you. And then we're going to put a ball and beam, 2 ball and beam papers in the group based on the ball and beam project that I wanted you to do. So you're going to have an introduction, a modeling of the system, which is derivation of the transfer function, which I'm going to ask you to look up. We're going to fill in the values for the mass and so forth. And when we get the transfer function, then we're going to apply 3 methods of control to the ball and beam. And then we look at the results that we get. And then the results that we get, we're going to discuss them. To say which one is better, which one is worse, which one, etc. And those 3 things will constitute your grade for the entire course. All right?
Yes, sir.
Yes, noted, sir.
Huh?
No, I'm saying noted, sir. Thanks.
All right. So these are the things that you're going to be working on as of today. Okay? So as of today, you're going to be working on these things. And as of today, we don't really have anything more lecture-wise to tell you. There is no more matter for you to pull. We good?
Yes, sir.
I don't hear anything.
Yes, sir. Yes, sir.
All right, so let's stop it here for today. So that, and then, so next week, 5 o'clock. But next week, 5 o'clock is just if there's anything for you to discuss with me. All right?
Yes, sir.
Okay then, sir.